Hello? Hello?
Hello?
How's it going?
Good.
We've got a few minutes before we start. Let me just see how everything is going. Okay, looks like we're up to 4 people. Okay, it looks like there's one new person who was not on the email list before. So I just gotta make sure. Oh no, let's see if everything's good. Okay. All right. It is 12 o'clock. How are people doing? Hello?
Professor.
Okay, could you speak again? It looked like there was some issue with the computer processing.
Okay, sorry. Hi, Professor Miller. Can you
Hi.
hear me?
Yes, I can. How are you doing?
I'm doing well, thank you. How are you?
Good. And I've got 2. What's this? And then there was a reminder that if you are speaking, to make sure you unmute so that you can be heard.
Mm-hmm.
Okay, can people see the slides?
Yes.
Yeah.
Okay. I know how challenging it is trying to find times for everyone. I'm trying to disable a little bit the video on my end, just because if you don't see me pacing back and forth, it actually decreases the file size significantly. Because now all it has to do is just process the slides, and that will hopefully allow it to post faster. Okay. So continue where we left off. I click it not working. Okay, there we go. Okay. So the goal today is to do the mathematics we need to get to RSA. So RSA is named after the three mathematicians who are given credit for discovering this. So this is Rivest, Shamir, and Adelman. Now, one of the things you've got to be very careful about whenever you do anything with cryptography is to distinguish between what is publicly known and what is true. So a lot of times, it turns out that some of the spy agencies knew things before the general public. And I'm not really going to get into who knew what, when, and where. But I will say, if you look at some of the histories online, some of the British agencies knew a lot of the stuff I'm about to say at other times earlier. Some of the greatest successes in World War II were due to the efforts of the Allies in cracking the German and the Japanese codes. After World War II was successfully concluded, however, it was still years to decades before it was publicly admitted how successful the cryptographers were. The war was over. Why would people keep that information a secret? So any thoughts? So why would you still keep it a secret even though the war is over?
Like maybe there's moral issues involved.
There's more, I'm sorry, there's more what?
Like moral issues involved.
Okay, in what sense?
Or people can use that in the next war.
People could use that in the next war. And so you don't want people to know what your true capabilities are. So even though World War II was over, a lot of the countries did not want other countries to know that they could do certain things. So frequently there are codes that are compromised, but it's not going to be publicly admitted that the codes are compromised. Also, let's say it becomes public knowledge next month that it's very easy to factor numbers. So we find a way to factor numbers, and now all codes that are based on factoring are no longer secure. So if that's the case, people will immediately shift to new types of codes. Is there any harm in the NSA or other agencies to admit, say that they've known for 10 years that factoring is easy, because now everybody knows factoring is easy? The NSA could admit that they've known for 10 years factoring is easy if somebody else admits that they can do it? Or do you think they still have to keep it secret that they knew factoring was easy? This is, again, hypothetical. But what are your thoughts? if everybody knows how to factor easily, is there any harm in the NSA admitting we know how to factor easily?
No.
They're just admitting what everybody else knows, correct?
Yeah.
Yeah.
So you all fail. It's because if they admit for the last 10 years they've known how to factor, then what this means is all the players on the world stage will know that for the past 10 years, if they were using codes based on primes, the NSA had the ability to crack them and could make decisions based on that knowledge.
Oh.
So you've got to be extremely careful in everything you do. There's so many opportunities to accidentally give away information. And you might think, well, there's really no harm. Everybody can factor now. But then people will know that the NSA and other agencies had been making plans for 10 years based on the knowledge that they could crack these codes. And that the ongoing activities reflect that knowledge. So you've got to be extremely careful. So again, we don't know if it's easy or not to factor numbers. The RSA code, the RSA method, is based on the assumption that multiplication is easy and factorization is hard. It might turn out that there is an easy way to factor. If quantum computers can be built, they can factor easily. There's a lot of behind RSA. And so even if factorization becomes easy, we're going to see a lot of really good mathematics today. All right. So just to give us a little setup, the way it works is always the following. Alice is always the one communicating. She's always talking to Bob. And then either Charlie, for eavesdropper, is trying to intercept the message. And so what I'm going to do is I'm going to just show you the mechanics of how RSA works. And then later we'll see why it works. So Bob does the following. And again, I could have a subscript B on everything to just remind me that these are things that Bob is doing. But since Bob is the only one doing anything, just for simplicity, we'll ignore them. So Bob chooses 2 primes, and he keeps them secret. And he chooses a number D, and he keeps that secret. Now, these are small enough numbers that we could crack them later by just simple brute force. You should really think of, say, 200-digit numbers for P and Q, and D, say, a 400-digit number. Bob makes public the product of his 2 primes. And he makes public another number E. Now, E and D have a very nice relation. E times D is 1 modulo P minus 1 Q minus 1. So we talked a little bit about this last time. So imagine we have a clock with P minus 1 times Q minus 1 hours. It means that ED minus 1 is a multiple of that number. Now, how else can you view P minus 1 Q minus 1?
Phi PQ.
Excellent. It's the number of numbers relatively prime to P times Q. It's phi of PQ. So already we have a couple of questions. Is it easy to choose large primes? Is it easy to find a pair of numbers E and D such that E times D is 1 mod P minus 1 Q minus 1? You can check numbers are prime, and you can check that ED equals 1 mod P minus 1 Q minus 1. But if I start looking at 200-digit numbers, will I still be able to find such numbers quickly, or is this going to be difficult? Remember, it's absolutely essential at the end of the day that we have an encryption method and a decryption method that can run in a reasonable amount of time. If it takes 6 months to encrypt a message, that's useless. And here's how it works. Alice chooses some message, and it ranges from 1 to P times Q minus 1. And then what Alice does is she takes the message and she raises it. Oh, I'm sorry. It should not be M to the D. It should be M to the E. My apologies. It should be M to the E. So she sends m to the e mod n. And then Bob decrypts it by taking that number and he raises it to the d. And so I apologize, I flipped the subscripts D and E. It doesn't really matter, we can just change which one is which. E stands for decrypt, E stands for encrypt. And what you notice is at the end of the day, when the dust settles, we get the decrypted message is 195632041, which is precisely the message. So, at least in this example, everything works out. And the question becomes, how hard is it to do this calculation? So if we take m, which is going to be, say, a 400-digit number, and raise it to a 400-digit number, that's going to take so much time if we do it by brute force that the life of the universe will be over and done with before we make any significant progress towards calculating that value. I want to talk about today the mathematics that show why this works and show you why it works efficiently and quickly. Now, in practice, what you might do is you might use RSA to send a very long key phrase and then use like a binary cipher or an alphabet cipher from last class. And then those are much faster to do. And you can just choose one long key phrase. All right. Now, later in the course, when we start getting to original research, we're going to look at what happens if there are errors in transmissions. If you go back to a message encrypted in the Caesar cipher, if the letter is mistransmitted, does it really affect your understanding of the entire message? So what do you think? We have something encrypted with the Caesar cipher, and one of the letters, when we transmit, we are supposed to transmit a W, and we accidentally transmit a T. Does it change the message greatly or just a little?
I guess as long as the word is long enough.
Well, you know, we're sending many words. We're sending many characters.
Oh.
So if one character is wrong in the Caesar cipher, does it have a big change in the message or a small change in the message?
Small.
Very small.
Okay.
It only affects one character.
Yeah.
But let's look at what happens with RSA. Imagine instead of receiving 1212094773, we receive 1212094883. We get an 8 instead of a 7 in the second to last digit. Now, when Bob tries to decrypt it, instead of getting 195632041, he gets 121141028. Only 2 digits are the same. This is one of the great advantages about RSA, or one of the great heartaches of RSA. If there's even one small digit that's off, the error is going to be magnified tremendously. And essentially, the final message you have, how many digits, if you had 2 messages, and let's say every digit is equally likely to be a 0 through a 9, about what fraction of the digits of 2 messages will be the same? So what would you guess? So I send a message, it has 100 digits, and I randomly write down another 100 digits. How many of those random 100 digits do you think will agree with the digits in the corresponding spot in the original message?
You mean the expected number?
Yeah, the expected number.
Okay.
So if we have 100 digits, and I randomly write down 100 digits again, how many of those new digits do you think will match up with the original?
2. 10.
10. If I had 1,000 digits, how many do you think would match up?
100.
Basically, 1 out of every 10 digits should be right. So I've got a message that's very short, 1, 2, 3, 4, 5, 6, 7, 8, 9 digits. I would expect 1 digit to be the same. I got 2 digits. Well, when the numbers are so small, it's really tough to say, is this significant or not significant? I expect 1 digit to be the same. Getting 0 or 2 isn't that far away from 1. So in RSA, if you make a very small error, it's going to be compounded enormously. The whole message gets amalgamated together, which is wonderful. All right. So here are the implementation issues, and we've talked a lot about these already. How do we find large primes? Is it easy to find large primes? Can we do it in a reasonable amount of time? And for a different question, we can talk about security. How large do we need to take to have a reasonable level of security? The next thing is, how do we find the E and the D so that D is 1 mod P minus 1 Q minus 1? And then I guess I flipped the roles of E and D throughout this. How do we compute M to the D and M to the E efficiently? And then the last one is, can you determine the D for decrypt just from knowing E and N? Now, if you look at the second bullet point, we have ED equals 1 mod P minus 1 Q minus 1. If we knew P minus 1 and Q minus 1, it turns out it's very easy to calculate D knowing P minus 1, Q minus 1, and E. We don't know P minus 1, Q minus 1. We only know P times Q. Currently, there are no publicly known algorithms that can easily find D in this situation. All right, so the first theoretical ingredient we need is Fermat's little theorem. Have any of you seen a proof of Fermat's little theorem?
No.
Nope. Okay, excellent. This is a beautiful theorem. You might be more familiar with Fermat's last theorem. So his theorem is usually abbreviated capital FLT. And Fermat's little theorem, you normally do a lowercase l for little. All right, so just to review some notation, phi of n will be the number of integers from 1 to n that are relatively prime to n. So we talked about this last time. We showed that, if we take a prime, phi of p is just p minus 1. Because, if we take a prime like 17, then every number from 1 to 16 is relatively prime to it. And then we talked about how phi of pq is p minus 1 q minus 1. And one way to prove this is inclusion-exclusion. We can say, well, there's pq numbers. Some are multiples of p, so we subtract p. I'm sorry, q of them are multiples of p, so we subtract q. P of them are multiples of q, so we subtract p. And then we realize that we subtracted the number pq twice, so we have to add it back. When you multiply out p minus 1, q minus 1, you get precisely that. You get pq minus q minus p plus 1. So we don't need the next step, but, as a nice exercise, prove that if m and n are relatively prime, then if mn is phi of n, if p is any prime, then phi of p to the k is p to the k minus p to the k minus 1. And these two facts allow you to compute phi for any value. So if you had taken a class in abstract algebra or group theory, I would be able to use certain phrases to describe what's going on. Since we haven't, assumed any class like that as a prerequisite for the course, I'm not going to use that language, but I just want to alert you that, if you continue with math, if you take a class on abstract algebra or group theory, you will see a lot of this content again, and you'll see it generalized to other settings as well. All right, so here's the statement of Fermat's little theorem. So let A be a number that's relatively prime to n, then A to the phi of n is equal to 1 mod n. So a special case is if n is a prime. So if n is a prime p, then we get phi of p is just p minus 1. So we get a to the p minus 1 is 1. Now the other case we'll need is when n is a product of two primes. Then we get a to the p minus 1 q minus 1 is equal to 1 mod pq. So these are the only cases we need to know for RSA. And because these are the only cases we need to know, and because the goal of this is to do cryptography, I'm only going to prove these two cases. It's not that hard to take what we've done and generalize it to the case of arbitrary n. I'll leave that as a good homework problem to just test how well you understand these arguments, how well you can push. But it gives us a good opportunity to talk about how you build intuition and how you find out. So the first thing is to gather some data and get a conjecture about what you think might be true. And so after gathering some data, we're led to thinking that a to the phi of n is 1 mod n. And now how do we prove this? Well, sometimes it helps to build intuition by taking simple cases and say, what's the simplest n we could look at? And the simplest n is when n is a prime p, because then phi of n is very simple. It'll just be p minus 1. So it's natural to first try to understand what's going on in this case. And then, if we can handle the case of n is a prime p minus 1, what do you think the next simplest case is to study after we do n equals p? So what are your thoughts as to what the next simplest case is after we do n equals p?
The power of p.
Yeah, so one thing is to try n equals p squared. What's the possibility? There are two candidates for what to try next. One is p squared.
2p.
Not quite 2p, although you're very close. P times q, the product of two distinct primes. So if we can do n equals a prime, the next natural case to study is either to take the same prime twice and get p squared, or to take two different primes and do pq. Okay, so let's take the case when n equals p. So let's do the proof. So we're going to assume that the GCD of a and p is 1. Well, why do we want to assume that? Well, imagine a is not relatively prime to n. Imagine a is even and n is even. And a to the phi of n is always going to be a multiple of 2. And there's no way it can equal 1. In fact, more generally, if a has any factor in common with n, let's say 3 divides a and 3 divides n, then the left-hand side is always going to be divisible by 3, and the right-hand side will always have a remainder of 1 when you divide by 3. So we see that if we want a statement like a to the phi of n equals 1 mod n to be true, it's essential that a and n are relatively prime. So let's consider the case when n is prime and that a and p are common factors. So we can look at the numbers 1, 2, all the way up to p minus 1. These are numbers that are relatively prime. Now what we do is we take our number a and we multiply each factor by a. So we get a, 2a, 3a, all the way up to p minus 1 times a. And I claim that both sets are all the remainders modulo p. They're all the numbers from 1 to p minus 1 when you reduce the mod p. So one of them is very easy to prove. It's clear that the first one is just all the remainders from 1 to p minus 1 mod p by construction. So what we have to do is we have to show that if we look at a, 2a, all the way up to p minus 1 times a, that those will just be the same numbers just maybe rearranged when we look at the modulo p. So my first question is it possible for any of those numbers to be 0 mod p on the right? You know, could 3a be 0 mod p?
No.
Okay, why not?
Because p is like co-prime to a, and p, and is also co-prime to any integer from 1 to p minus 1.
Excellent. We know p has no factor in common with the numbers from 1 to p minus 1. It has nothing in common with a. It's a deep fact to prove, but if a prime divides a product, it has to divide at least one of the two terms. We know none of these numbers are going to be remainder 0 when we divide by p. But it is possible that two of the numbers could have the same remainder. So we just have to show that can't happen. And once we show that can't happen, because we have finite sets, if the p minus 1 values are all distinct mod p, then they have to take on all the p minus 1 values. This is not true if we have infinite sets. But because we have finite sets, if they're all distinct, they have to cover all possibilities. So let's imagine maybe I times a equals j times a mod p. So then if we subtract, we get I minus j times a is 0. Well, since p doesn't divide a, that means p has to divide I minus j. So it means I equals j mod p. So what this means is if we take two distinct values, then we will get two distinct values. You're not going to have distinct things mapped to the same thing. So now let's multiply everything together. If we multiply everything in the first set together, we're going to get p minus 4l. In the second set, we're still going to get a p minus 1 factorial because we have a 1, 2, 3, all the way up to p minus 1. But we're also going to get a factor of a every single time. And since we have p minus 1 terms, a to the p minus 1. So we get p minus 1 factorial equals p minus 1 factorial times a to the p minus 1 mod p. Can I cancel out the p minus 1 factorials from both sides?
Yes.
Yes.
Okay, so why can I cancel it?
Because both p minus 1 factorial, it's co-prime to p.
Because it's co-prime, I could subtract, formally p minus 1 factorial from both sides, and I would get 0 is p minus 1 factorial times a to the p minus 1 minus 1. And since p doesn't divide p minus 1 factorial, then p would divide a to the p minus 1 minus 1. I can cancel it out, and I get a to the p minus 1 is 1 mod p, which is exactly what we wanted to prove. So this handles the proof in the case when n equals p. What's really nice in this case is I know exactly what the residue classes are. 3 all the way up to p minus 1. Another case is I know exactly which numbers are relatively prime to p. If I were to do p squared or p times q, it would be a little bit harder. So in the general case, what I can say is the distinct remainders I have, the numbers I have will be x1 to x phi of n, and then I multiply everything by a. So you can go through the argument very similarly. So here we're just using labels for the different possibilities. We have phi of n numbers that are relatively prime to n. Let's call the first one x1, which will be 1, and so on and so on and so on. And I'll leave it to you as an exercise to show that the argument we gave above holds almost identically in this case as well. Now, we can prove it directly in the case when n equals pq. And we'll assume again that a is relatively prime to pq. Now, what I like about the proof that I'm about to show you is it highlights a wonderful math concept. Reduce whatever problem you're given to something that you know. So we just proved Fermat's little theorem when we have a prime. So what I want to do now is I want to use that. Well, I have n equals p times q. I have two primes. So here's the trick. I want to study a to the p minus 1, q minus 1. We can play games with the exponents. So we're going to apply Fermat's little theorem first with a to the q minus 1, and the prime will be p. And next with a, oh, there's a typo, it should be p minus 1, not p minus q, and with prime q. And what we'll get is we'll get, in the first case, a to the q minus 1, that's going to be our input number. We raise it to the p minus 1, and it's 1 mod p. And the second one, we get the same number, and that's equal to 1 mod q. So if I give you a number x and it's 1 mod p, and it's also 1 mod q, what do you think it has to be mod pq?
1.
Yeah.
If
1.
So definitely 1 could work. We need to just show that that's the only thing that can work. And this is a nice backdoor way to get the proof. So we know it has to equal 1 plus some multiple of p, let's call it alpha p. And it also has to equal 1 plus some multiple of q, beta q. So what we want to do is we want to show that alpha is a multiple of q and beta is a multiple of p. And if we can do that, then we'll get that it's equal to just 1 mod pq. So we first get alpha p is beta q, just by subtracting. Since p and q are distinct primes, p doesn't divide q, q doesn't divide p, so alpha must divide beta. P can't divide q, so p has to divide beta, and q has to divide alpha. And that's exactly what we wanted to show. And so we do get that a to the p minus 1, q minus 1 is 1 mod pq. Okay. Was there a question or?
No.
Okay. So I really like this proof because it really minds what we had before. It avoids introducing more notation. And it gives you an idea of where it's coming from. It's coming from the special case of when it's a prime. The challenge is figuring out how to apply it. So we apply it twice, and we use the a to the q minus 1 and a to the p minus 1. Now, it's out that you can use Fermat's little theorem as a primality test. It's not a perfect primality test, but it's not a bad one. And it works as follows. Imagine you have a number a such that the GCD of a and n is 1, and you calculate a to the n minus 1, and you don't get 1 mod n. Maybe you get 3 mod n. Then n can't be prime, because we know if n is a prime, then a to the n minus 1 has to be 1 mod n. So if you ever get something other than 1, it's proof that n must be composite. Unfortunately, if it equals 1, it doesn't prove that it's prime. It just proves that it might be prime. So has anybody seen this as a primality test before?
No.
Okay. So this is the strangest primality test I can think of. So consider the number 105. It's 5 prime. What do you think? Is 105 prime?
No.
No, why not?
Can be divisible by 3.
Okay. What about 2992?
You're 99.
2.
So that's 2992. Is that prime?
Because that's even.
Yes.
Even.
Yeah, even.
What about 5995?
It's divisible by 11.
Divisible by 11, also divisible by 5. 7997 is divisible by 11. So in all of these cases, the way you tell me a number is composite is you give me a factor. Look at what Fermat's little theorem does. If it equals a number other than 1, then it must be composite, but you don't know a factor. To me, this is very strange. You can be sure that a number is composite without knowing any number that divides it. Okay. Now, it turns out that if n is a 400-digit number, it could be a computational nightmare. So very shortly, we can actually do these calculations very quickly. So taking high powers turns out not to be a problem. Even though it only gives you candidate primes, most numbers that work, at least that work for many terms of A, are going to be primes. Unfortunately, there are a couple of numbers that will always pass this test no matter what A you choose, but are composite. These are now known as Carmichael numbers. The smallest one is 561, then 1105, and so on and so on and so on. So there's a lot that's known about these numbers. A lot is still mysterious, but we can prove that there are far, far fewer Carmichael numbers than primes. So if your number is large and it's passing the test, almost surely it's prime. But if you need to be absolutely sure, what you can do is you can use Fermat's little theorem to quickly get some good candidates, or method to just be sure. All right. So what I want to do now is I want to talk about how would we raise a 400-digit number to a 400-digit number quickly. So let's think about multiplication and addition. You want to think about 400-digit numbers. So imagine you wanted to add two 400-digit numbers. Approximately how many additions are there if you add two 400-digit numbers?
400.
400. Maybe double that because maybe you have some carrying to do. But it's basically on the order of 400. If you had two 800-digit numbers, how many operations would it be?
So 800.
800.
400.
And if you had D digits, how many additions would it be?
D.
D.
D operations.
So if you add two D-digit numbers, the cost of the addition is growing linearly with the number of digits. Let's say you wanted to multiply two D-digit numbers. How many multiplications are needed to multiply two D-digit numbers?
I guess D squared.
Yeah, and you're going to have a good as well. But this is why you can see multiplication is so much more expensive than addition. If you have 2,000-digit numbers, it's about 1,000 additions to add them, but it's about 1,000,000 multiplications. So when we are looking at the cost of algorithms, for a lot of things we only care about how many multiplications. Because the multiplications can be so much slower than the additions are essentially free. So if we look at a specific function, let's say we look at the following polynomial, 3x to the fifth minus 8x to the fourth plus 7x cubed plus 6x squared minus 9x plus 2. I'm only going to deal with the multiplications to try to figure out how expensive is it to evaluate. So I might want to figure out what is it when I take x equals 2 or x equals 7 or x equals negative 5. And I want to see how many multiplications are needed. So the naive way to evaluate something like this is you evaluate each term and then you add. So if I want to calculate 3x to the fifth, that's going to be 5 multiplications. The x is 4 multiplications and then 1 more to do the 3. So the total cost is going to be 15. 5 plus 4 plus 3 plus 2 plus 1 plus 0. So it turns out these are the triangle numbers. And if you had something of degree d, it would be d plus 1 over 2. Has everybody seen why the sum of the numbers from 0 to d is d plus 1 over 2? Is there anybody who hasn't seen this? Okay, they sometimes talk about the story about how Gauss saw this when he was 5 years old. And the teacher wanted to get the kids, to just shut up for a little bit and said, add up all the numbers from 0 to 100. And Gauss quickly noticed that the answer must be 5,050. And one way to prove this is take the numbers from, say, 0 to d, and then write them backwards from d down to 0. And if you add them, you'll get d plus 1, d plus 1, d plus 1 each time. You'll get d each time, plus 0, d minus 1 plus 1, d minus 2 plus 2. So sum is going to be d. We have a d plus 1 time. That's why it's d plus 1 over 2. And then just writing this out explicitly, here's my numbers 1 to d, writing it backwards, and then I'm going to guess d plus 1 each time, and I'll have d of them. So it always comes down to, are you including 0 or not? It doesn't really matter if you include 0, because adding 0 is not going to change the sum. All right. So if we do a brute force evaluation of a polynomial degree d, it costs us roughly d squared over 2 multiplications. So this is growing quadratically in d. This is very expensive. What I'm going to show you now is Horner's algorithm is a much faster way to evaluate polynomials. So this is one of my favorite algorithms of all the stuff I've ever seen in mathematics. So we take the same polynomial, and I'm going to show you how to do it much faster. And the idea is that you don't want to keep doing the same thing again and again and again. If I calculate x squared, x cubed, x to the 4th, and x to the 5th, notice a lot of the calculation of x to the 5th is similar to what I'm doing for x to the 4th. If I know x to the 4th, I just have to multiply by x, and I get x to the 5th. So I shouldn't be independently computing each term. I should compute each term and use that calculation to help get the next one. And so this is where we get the nested polynomials, the nested parentheses. If you look at what's going on, we have 3x minus 8 times x plus 7 times x plus 6 times x minus 9 times x plus 2. If you look at 3x, it's then hit with 4 more x's. That's going to give us a 3x to the 5th. And if you look at the negative 8, that hits 4 x's. That'll give us a negative 8x to the 4th. If you look at the 7, that 7 is going to hit 3 x's, and you'll get 7x cubed, and so on and so on and so on. And what you can see now is this is only going to cost us d multiplications. So this is incredible savings from something that's quadratic in the degree to something that's linear in the degree. So there's many applications of this. One of the best applications I know is if you are interested in fractals, we often use an algorithm like this to evaluate the polynomials that we use in iteration very, very quickly. Now, while this is a great savings, it's not quite enough yet to make multiplication tractable. And the problem is, if it's linear in the degree, it's still going to be very painful to calculate some of this. If I give you a number that's of size 10 to the 400, and I want to calculate x to the 10 to the 400, that's going to cost me 10 to the 400 multiplications. So in our first lecture, we talked about, I think, when we looked at alphabet codes and the general permutation, just if you had a universe of computers, and just how large these numbers are, correct? Yeah, so it's hopeless to do a linear algorithm for something of size 10 to the 400. You can't do 10 to the 400 operations. So while Horner's algorithm is a tremendous improvement, it's not enough to make things practical. So the question is, what else can we do? Trying to evaluate a general polynomial, we can't really do better than Horner's algorithm. So the hope is maybe if we look at a special polynomial, we'll be able to do better. So any thoughts about what the simplest polynomial degree D is that we could look at?
X to the d power.
Yeah, x to the d.
Yeah.
So take a pure monomial x to the d, and maybe there's a fast way to do just that. So we'll try polynomials in the form, I'll do x to the n. And a clever idea is to write n in binary. So I always use 100 as my example because that way I'll remember. So 100 is 64 plus 32 plus 4. So when you write things in binary, instead of going with digits 0 through 9, our digits are just 0 and 1. And then the first place is the ones place, then you have the twos place, then the fours place, then the eights place, then the 16s place, and so on and so on and so on. So the way I would write 100 in binary is it would be 1100100, and the subscript 2 is to tell us that this is not the number 1,100,100, but it's a number where these are the binary digits. And just like in 100, that means 1 times 100 plus 0 times 10 plus 0 times 1. Here it's going to be 1 times 64 plus 1 times 32 plus 0 times 16 plus 0 times 8 plus 1 times 4 plus 0 times 2 plus 0 times 1. And now here's how you do things incredibly rapidly. X times x is x squared. X squared times x squared is x to the fourth. X to the fourth times x to the fourth is x to the eighth. X to the eighth times x to the eighth is x to the 16th. X to the 16th times x to the 16th is x to the 32nd. X to the 32nd times x to the 32nd is x to the 64th. So how many multiplications have we done so far?
6.
We've done 6. So we keep x to the 64, because we need that. Then we multiply that by x to the 32, that's 7 multiplications. And then we multiply by x to the 4th, that's 8 multiplications. We can calculate x to the 100 in just 8. That is tremendously better than brute force. Brute force would have been 99 multiplications. So in general, can anybody tell me what's the worst case? How many multiplications would you need? So in general, somebody tell me if I have x to the n, how many multiplications would I need? What's the worst case?
Worst case. So log 2n.
So log of n base 2. Is that what you mean by log 2n?
Yeah.
Okay, almost. It's not the log of n base 2. It's close to that. Or is it that? I'm trying to think if it's twice log of n base 2. Because you might have to multiply by all the stuff coming up to it.
Oh.
Right?
Yeah.
So the worst case is if we then have to do all the multiplications
Yes.
afterward. Right?
Yeah.
You want to be very careful with your estimates. That, sometimes you might forget things and you want to make sure it's not going to hurt things. Well, imagine we actually had x to the 127. So we would have to then multiply everything, and in 8 it would be 11 multiplications. Can you think of a faster way to calculate x to the 127?
Maybe fast way.
X to the 128 over x.
Beautiful. So sometimes it's actually better to overshoot and then correct with division. But we're not going to do division. Let's just say worst case is going to be twice log of n base 2. Well, this is tremendous. We go from something that takes order d squared over 2 to something that takes order d to something that takes order the log of d base 2. So if we want to calculate the log of 10 to the 400, that's nothing base 2. You know, this will then be 400 the log of 10 base 2, maybe double that, so 800 log of 100 base 2. So log of 10 base 2. Can somebody give me approximately the value of the log of 10 base 2?
It's about 3 point.
Yeah, it's 3 point something. So why do you know it's 3 point something?
Because it's between 8 and 16.
Yeah, it's between 8 and 16. So 800, the log of 10 base 2, you know, 800 times 4, it's going to be almost 3,200. I can do 3,200 multiplications, or my computer can do 3,200 multiplications. I'm not worried about that. I am worried about doing 10 to the 400 multiplications. This is the miracle of fast multiplication. It takes something which would initially look completely intractable, and in this special case, reduces it so tremendously that we can now handle the calculation in a reasonable amount of time. Okay. Any questions on fast multiplication?
No.
If it weren't for this, we could not do RSA in reasonable amounts of time. Okay. So just recapping, as I mentioned, Horner takes us from d squared to d. Fast multiplication brings us down a logarithm. And so these are very cheap to do. So the last bit of theory to introduce for tonight is the Euclidean algorithm. Have any of you seen the Euclidean algorithm?
Yes.
Okay, that was one yes.
No.
Okay. All right, so let me show you the Euclidean algorithm. Two of my colleagues have a debate, you know, which is better, the Euclidean algorithm or the trefoil knot? To me, it's not a debatable question. The Euclidean algorithm is just so tremendously important. So it takes as input two numbers, x and y, and for definiteness, let's say y is greater than x.
Mm-hmm.
The goal is to find the greatest common divisor of x and y. And the way it does this is it finds a and b such that ax plus by is the greatest common divisor of xy. So there's lots of ways you can prove that such a formula exists. There are some non-constructive proofs. But for what we're going to do for RSA, we actually need to know the values a and b. So I'm going to give you a constructive proof. Now, before we do that, let's think a little bit about finding the greatest common divisor of x and y. Theoretically, is it hard to find the GCD of two numbers? So I don't care if the algorithm runs quickly. Can somebody give me a way to find the GCD of x and y?
Probably the most brute force way is like calculating all the divisors of x and like the prime factors of x and y, and then multiplying the common ones together.
Great. So one way is to factor each number. The thing we could do is we could see, we start off, you know, does x divide y? If it does, we're done. If not, look at x minus 1, then x minus 2, then x minus 3. And keep going down until we find the first number that divides both. Because we know the greatest common divisor can't be greater than x. So multiply all the numbers from x down to 1. So theoretically, it's trivial to come up with an algorithm to find the GCD. But if x is of size 10 to the 400, this is useless in terms of runtime. So we want to find a fast way. So to just make notation a little bit easier. Hello? Okay. So to make notation easier, let's let R0 be y and R1 will be x. So what we're going to do is we're going to use just the simple division rule. So R0 is going to be some multiple of R1, Q1 R1, plus a remainder. So if I want to take, say, y equals 17 and x equals 5, I can write 17 as 3 times 5 plus a remainder of 2. And then clearly the remainder has to be between 0 and strictly less than R1. Because if R2 happened to be 1, if there was a remainder of R1, then we would just increase the multiple by another 1 and we would have Q1 plus 1. All right? And then we just keep repeating. Now we can write R1 as a multiple of R2.
Yeah.
Oops, that should be an R3, not R2 there. And then we continue, we keep going down and down and down until eventually we get Rn is Qn plus 1, Rn plus 1, plus Rn plus 2, and Rn plus 2 is either 0 or 1. And then here are a couple of things for you to do as homework problems if you want. First is to note that the greatest common divisor of R0 and R1 is the same as the greatest common divisor of R1 and R2. And then lather, rinse, repeat. But as you keep marching down, you don't change the greatest common divisor. So again, if you want, these are great things to try to prove, for practice. And then you can climb upwards to get A and B. So I'm not going to go through how you would climb upwards. I will leave that as another homework problem as well. What I would say you should do is take two somewhat large numbers, say maybe 217 and 381, and apply the Euclidean algorithm, and then see if you can figure out how to get A and B. We are not going to really do any research on RSA, so for us it's not really absolutely essential to know how to do this. But it's good theory, it's good exercises for you to try to think about as to how can you make this explicit. And if not, if you do a Google for this, there are plenty of resources online that give you the proofs of this. All right. So now we're ready to come to the last section for today, implementing RSA. So before we do that, are there any questions about what we've done so far?
No, for me.
No.
Okay.
No.
So now it comes time to show why does RSA work. So the first thing is we have to choose two large primes. Use Fermat's little theorem to quickly get some candidates. And so if these numbers pass Fermat's little theorem, lots of A's, then we can be reasonably confident that they are primes. And then, I'm not going to go into it, but there are some fast deterministic methods that exist now to prove that a number is. So there's a beautiful paper called Primes P, or Prime, the Primes is P or Primes? I think it's, Primes is P. It's from around 2002, and it was by an Indian computer scientist and his two undergraduates. And they came up with a fast, deterministic way to tell if a number is prime. There are faster ways, but those ways rely on some unproven assumptions. They're assumptions that most mathematicians believe, like the Riemann hypothesis is true, but they're still conditional proofs based on things we don't know. Now, we talked earlier about trying to find the E and the D. Here's where we use the Euclidean algorithm. We want to find two numbers such that when we multiply them, we get 1 mod p minus 1 q minus 1. Or we get 1 mod phi of pq. So let's take x to be E and y to be p minus 1 q minus 1. Then if we use the Euclidean algorithm, we get a times x plus b times y is the greatest common divisor. All we need to do is make sure that E is relatively prime to p minus 1 q minus 1, and we win. If not, we increase E by 1 and we try again. And then it's an interesting question, how many numbers in a row can you have sharing a factor with p minus 1 and q minus 1? So that's a little bit more involved, but I'll leave that as another exercise for you to think about. And it can be shown that you don't have to wait that long. But the amount of time you need to wait is, I believe, proportional to the logarithm of p minus 1 and q minus 1. And then we use fast multiplication to compute m to the e mod pq. So that really should be m to the d. So later tonight, I will fix all of this. All right. So all that's left now is proving that when we calculate these things, we actually get the message in the end. So I'm going to go back to the slides over here. So again, I apologize that E and D are flipped. I will flip them later. We calculate m to the d mod n. Okay? You have to think of m and d as being 400-digit numbers. So these numbers are huge. But we can use fast multiplication, so it's not that bad. And then we want to take this whole number and raise this to the eth power. The idea is, since we want to look at things modulo n, I can keep reducing by n every time I do multiplication. Right?
Yeah.
So, we had okay, so when we had the stuff over here, oops, and I was calculating all these powers, I can do mod n here, 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 mod n here. And that's fine. I can do mod n as I go throughout and then do mod n again at the very end. So when I'm calculating things, it's not so bad with the mod n's. And now we want to calculate m to the d, raise that to the e, so we get m to the ed mod n. So how would we calculate m to the ed mod n? Well, this is where we use ed as 1 mod p minus 1 q minus 1, and then we use Fermat's little theorem. So the final problem for you to think about, put all the pieces together and show that when we do all of this, we will get the original message back when we're done. And it comes from the fact that if we have m to the ed, it's really the same as m to the 1 plus a multiple of p minus 1 q minus 1. And by Fermat's little theorem, m to the p minus 1 q minus 1 is just 1 mod big N. All right. So this is a good place to stop in terms of new theory. We have done a tremendous amount tonight. This is a huge amount of a course in abstract algebra. We did Fermat's little theorem. We proved it first in the case of a prime, and then showed how to generalize that to a product of two distinct primes, or to generalize it to just any number n. We talked about fast multiplication, we talked about the Euclidean algorithm, and we talked about how all these pieces tie together and give us RSA. So absolutely tremendous. So the only thing left, and let me just stop sharing the screen right now. Oops. I'm just trying to kill the sharing screen. Are people still able to see my screen?
Yes.
Yeah.
Yeah.
How about now?
No.
Okay. So we've talked about how to do RSA, but the big question is, can you trust what you're receiving? So imagine you get a message from Alice. How do you know the message really came from Alice? So that's the last thing to think about for tonight. So Bob makes some information public, and then anybody in the world can contact Bob, and they can send a secure message. And so Bob gets a message from somebody claiming to be Alice. How does he know he can trust that message? So ideally, Alice would know some information that only she and Bob know. And Alice could put that in the message. But maybe somebody else knew that information. Or maybe Alice and Bob don't have any common secrets. Imagine you're trying to buy something on Amazon, or better yet, some new website that you've never gone to before. You authorize your credit card company to transfer the money. You're going to sites you haven't gone before. You need to be able to prove your identity. So it is essential for Alice and Bob to be able to what's called digitally signed messages, so that there is a way for Bob to know that the message came from Alice. So does anybody have any thoughts as to how we could do that? So it turns out that the error I made is actually useful in figuring out how to have Alice prove to Bob that she is who she says she is. And it goes as follows. So let me go back now. Okay. So can people see my screen again?
Yes.
Okay.
Yeah.
So we're going to go back, and you know how Bob has made all this information public?
Mm.
And I talked earlier about how we could have subscripts B for Bob. We can do the same thing with Alice. Alice can choose 2 primes, and Alice can choose an N. We can have subscripts A for Alice. And so what Alice can do is she can write a message for Bob using Bob's stuff. And at the end of her message, Alice writes a short note saying, "Hi, this is Alice." And she encrypts it. But now we're going to use a wonderful property of the real numbers. multiplication is commutative. It doesn't matter 3 times 5, 5 times 3, they're the same thing. We saw a little bit of this when we looked at Fermat's little theorem. When we looked at the proof over here, we saw that we could do it as either q minus 1 times p minus 1 or p minus 1 times q minus 1. So what happens now is Alice chooses her own primes and everything, and at the end of the message, she writes the short note, "Hello, I'm Alice," and she encrypts it. Now she's supposed to raise it to E for encrypt, but she will raise it to the dth power for decrypt. And then she includes that in her message, and then she raises that message to Bob's encrypt thing. Now Bob tries to decrypt the message. He raises it to his decrypt, and the beginning of the message now decrypts nicely, but then he gets to the part from Alice, and it doesn't decrypt. It's still gobbledygook. Now, normally you can't decode a message from Alice, because you don't know her decrypt key. But because Alice encrypted it with her with her D for decrypt, Bob can now raise it to the eth power, which is publicly available, Alice's public decrypt key, and that will fix things. So I'll let you try to go through and put this down clearly and put in all the details. The symmetry in what's going on allows us to digitally sign messages, and if you can trust that this public site is truly Alice, then only Alice would be able to put in a message, "Hello, I am Alice," and be decrypted by raising it to the east of Alice. Okay. Any questions on this?
No.
Okay. So again, right now the goal is to just show you guys some really good mathematics. And then after this, we're going to then start moving to eventually some research. But before we get there, I want you to get some rough sense of what's out there in cryptography, as well as what's out there in terms of mathematics. How do these things fit together? How do we attack problems? Those are going to be the transferable skills that will serve you for the rest of your life. All right, I'm going to fix all the stuff, and then later tonight I will upload a corrected version of the slides. I'm going to try to start the sharing screen again. All right, have a great evening, all.
You too. Thank you.
You too.
Yeah,
Bye.
you too. Thank you.
Thank you.